Okay, what we need to do, what we're looking at now is two laws which are called Kirchoff's laws. First, we're going to find out a little bit about Gustav Kirchoff. He was born in Königsberg in Russia in 1824 and he died in Berlin in 1887. And I'm sure you're wondering what he looked like. Imagine what most men scientists looked at that time. And if your idea was something like this, then yes, you're correct. They all look pretty much the same. Anyway, he came out with two laws to do with current and voltage. The first one is the charge flowing into a junction, in other words, the current going into a junction, will be equal to the charge flowing out of the junction. What goes in comes out. Okay, that's the first law. That was to do with current or the flowing charge. The second one is in a complete circuit loop, the sum of the EMFs in the loop is equal to the sum of the potential differences in the loop. In other words, the energy that's given by the cell, the battery, or whatever, will be used up by the components in the circuit, in the loop. Okay, so you basically have to take one loop and all the voltages will add up. One way of looking at it is that the sum of the voltage will also be equal to into zero, because one's going to be positive and all the others are going to be negative in that sense. So let's look at Kirchoff's first law, sometimes known as Kirchoff's current law. So the charge flowing into a junction will be equal to the charge flowing out of the junction. So the flow of charge is called the current, as you know. Basically the current going into a junction is equal to the current going out. And therefore, for any junction, the sum of the currents will be equal to zero. And we're looking at a specific example here. Let's take this junction there. There are two currents going in and there are two currents going out. The sum of the currents is going to be equal to zero. Let's say the currents going in are going to be positive, and we say that the currents going out are going to be negative. So in we've got I1 plus I2, out we have I3 plus I4. We add them all together, it's going to be equal, adding up to 0. Or you could say that I1 plus I2 is equal to I3 plus I4. Now we need to look at Kirchoff's second law, which is the Kirchoff's voltage law, let's say. And here he said, in a complete circuit loop, the sum of the EMFs in the loop is equal to the sum of the potential differences in the loop. The EMF, or the voltages, the PDs, is basically the energy per coulomb. All these PDs must add up. The sum of the EMF must equal the sum of the PDs around the circuit, and since the PD is energy per coulomb, all the energies must add up. So it's basically another way of expressing the conservation of energy. The energy that's given by the battery or the EMF will be used up in the circuit. Now we've got one source of energy, which is the EMF. This PD, this EMF, is equal to the sum of the PDs around the circuit. So EMF here is going to be equal to PD1 plus PD2 plus PD3 plus PD4. And that's what we find out. But we know that the potential difference V is equal to IR. And so what we can do is, if we know the current and we know the resistances, we know that this is going to be IR1, because that's the resistance of that internal resistance there. This is IR2 and IR3 and IR4. Notice that the I is always going to be the same value because it's one current loop. So one way of writing it would be EMF is equal to IR1 plus IR2 plus IR3 plus IR4. Now we're going to look at a problem from a textbook. We're going to unite these two laws together. We need to find all the currents in this circuit. Now maybe you can't see so well. This is 3 volts, this is 3 ohms, 9 ohms and 6 ohms. First we need to define the currents. Let's say this is I1 and and we can define those as I2 and I3. Secondly, from the Kirchoff's current law, I1 going into this junction here will be equal to I2 plus I3. This current will divide into I2 and I3. That's easy enough to see. The second one is we look at a big loop, which is the big loop there, which I'll label like this, going anti-clockwise. And we need to define the second loop, but it doesn't matter which way, as long as you're consistent with the directions of the current. Then we have this second loop there. Loop 1. So you know that the EMF is equal to the sum of the voltages, the sum of the IR. So the EMF, you know, is 3 times by IR, which is 3 times I, 1, plus 9 times I2. We'll call that equation 1. What about loop 2? It's going this way. What is the sum there? Well, there's no actually EMF here, but what we do know is that the sum of the EMFs is equal to 0 in this case. So 9 times by I2 minus 6 times I3 is equal to 0. Or you could say that 9 I2 is equal to 6 I3. And let's look at Kirchoff's current law. We know that I1 is equal to I2 plus I3. But let's look at this. We have three unknowns, I1, I2, I3. We have 3 equations. How can we solve that? This is your favorite mathematical exercise, simultaneous equations. Yeah. So we'll take equation 1 and we'll substitute in 3. The reason for this is that I want to get rid of I1 there. I know that I1 is equal to I2 plus I3, so I'm going to substitute that in there. So I end up with 3 is equal to 3 times I2 plus I3 plus 9 times I2. So we end up with this, which is equation 4. Now, if we double this, we end up with 6 is equal to 24 times I2 plus 6 I3. I haven't done this by chance. I do this basically because here we have an expression with I2 and I3, and this is negative 6. This is plus 6. Yes, you've guessed it. We have to add them together, and the 6 I3s cancel. So we're going to add 2 to 5. So we end up with 2 is 9I2 minus 6I3. Add this to this, this to this. So we end up with 6 is equal to 33I2. And that's that. How to find I2? Divide both sides by 33. And this gives us I2. And once you have one value, then it's easy to substitute that value into the others and find. It's easy to find I1 and I3 because you already have I2. This is the kind of problem that we need to do, and you need some practice at doing this. In line with the academic honesty of the school, I give the references of the websites that I use and the textbook that I use to do this.